Now, we will come across different terminology for antenna array, and some of the terminology are to explain you different type of antenna array. So, I have tried to classify this antenna arrays based on certain things which I am showing you here. The first classification means we are naming some antenna arrays, different type of antenna arrays based on the spacing and excitation parameter, because space and excitations are controlling parameter of the antenna. If they are dominating, if we are considering them as the prime parameters, then how the antenna arrays are named. So, based on this you will come across an antenna array called uniform antenna array. So, uniform antenna array is a common terminology you will come across when you just pick up any book, start reading antenna array, you will find uniform antenna array. So, as the name implies uniform, usually it takes identical elements, space between elements are same spacing. So, identical elements, so when I say identical means if I am taking an array of 10 elements and the first element is dipole, obviously the other 9 elements are to be dipole. Usually this is the approach. So, identical element, if one is lambda by 4, the other 9 are to be lambda by 4. So, length wise also they are same, element wise they are same, spacing is uniform, equispacing. So, if it is D, not that one is D by 2, another D by 4, another is D, it is not like that, it has to be D. They will be excited in the same amplitude, there will be uniform phase shift. So, if these conditions are satisfied, then you will come across an array which is called uniform antenna array. Okay. Again, we are going for the placement of the array, then you will come across linear, planar already which I have explained. So, we can skip this because this is the placement of the antenna array. Then coming to the space parameters discussion. Based on the space parameters, how you are going to define the antenna array. Initially, if you see amplitude of excitation, this spacing, this is basically the circuit concept. Based on the circuit concept, we define that it is a uniform antenna array. Next, it is the distribution of the elements, the linear distribution, planar distribution, triangular distribution, that way we are naming the antennas array or different antennas array. Now, we are looking for the based on the space parameter, that means our prime attention will be based on the pattern, and based on the pattern how do we classify the antenna array. So, in that group the first group is the broadside antenna array. It is a broadside antenna array. If you see here the principal radiation, that the maximum radiation is perpendicular to the array axis. For example, if you have the elements placed like this, this is the array axis, then if the radiation takes place perpendicular direction to the array axis, that means in this direction or in this direction, it may be bidirectional, it may be unidirectional, but direction should be perpendicular to the array axis, then this type of antenna array will be named as broadside antenna array. It is broadside antenna array. The condition here is that the elements should be equispaced. Why I am telling you from where I am getting these things, let me just give you a background. When we express a particular strength at the point of interest, we have the amplitude, then the phase, which we name it as e to the power minus j psi. Now, this particular phase is due to the path traveled by the signal. So, it is 2 pi by lambda, that is k. Then the path difference is d cos theta. If you are going for like this, suppose your array is aligned like this 1 2 3 4 like this, this is a distance, this is a distance, they are making angle theta, then this distance let us say it is d, then it is your d cos theta, the separation between these two is the d cos theta. That d cos theta is the path difference, multiply with that k 2 pi by lambda gives the phase. This phase is due to the path. Then you have an additional phase which is the excitation phase. You have two phases now. One is your due to path, another is due to excitation. Okay. So, now this k d cos theta plus beta if we are going for the upward direction where this is maximum, then to get the amplitude maximum this should be 0, this should be 0. So, if we make this 0, then k d cos theta plus beta should be equal to 0, but in which direction you are now trying to find out? It is perpendicular. So, that means theta is equal to pi by 2. If we substitute that, it implies beta is equal to 0. So, this is what is the one of the conditions, that all in same phase, sources are in phase, that means each element will be fed with the same phase. This is a mandatory condition for having a broadside array. Look into this animation. This is 4 slot antenna array. It has a feed network. Look into the feed network, how it is going. Start, your 50 ohm is at the bottom, because that 50 ohm will be connected to the source. Then it is going to match the different impedance which it is encountering in different point. It is 135 ohm. So, it is matched. So, by maximum power transfer theorems, you are getting maximum signal here and also delivering the maximum signal, because this location, this patch or this slot is giving an impedance of 135. So, directly if you connect a source, it is mismatched, it will not match. So, that is why you have to take help of the feed network. This feed network are the transmission line. These are microstrip patch transmission line for this particular example. So, as you know, length and width controls the L and C. So, the L and C is controlled by this. Based on this, a matching condition is generated. So, R plus Jx, the X is controlled, and accordingly you get a impedance. That impedance matched with the patch, and you are feeding the patch in this location. And this feeding, if I say this is the axis of the antenna, then I have a radiation which is in this direction, perpendicular direction. So, this is a broadside radiation. Okay. So, you mark there are certain side lobes also, minor lobes, but this is a situation like this. All right. Usually the elements, this is also a requirement when you are designing the broadside array, you have to keep certain things in your mind. The phase has to be 0, the excitation phase has to be 0, then that means it has to be fed in same phase. Preferably you should keep your element perpendicular, like you have a dipole. Dipole can be kept like this, dipole can be kept like this. So, if you are going for a broadside array, keep your elements perpendicular to the axis, so that it radiates and meet in this direction. If you are keeping like this, then this radiation has to be again oriented to give you a broadside direction. All right. So, that is why usually the elements are placed perpendicular to the direction of the axis. The pattern may be bidirectional, like I showed you here, this pattern may be bidirectional, but many of the applications they prefer the unidirectional approach. And to avoid the grating lobes, the spacing between the elements should not be multipool of lambda. It should not be n lambda, where n is 1, 2, 3, 4. It should not be lambda, it should not be 2 lambda, 3 lambda, should not be. What do you mean by grating lobes? Already I have explained you major lobe, minor lobe, back lobe, all those things we have discussed in your class. Grating lobes are the minor lobes which are almost all having the same amplitude as the main lobe. So, that means multiple maxima when you get, like the pattern which you saw in my initial slide, this is a situation of the grating lobes. The previous slide if you see, this is a situation of the grating lobes, that almost all are of equal amplitude, all right. So, if you are and this is already explained, if you are having a lambda or 2 lambda type of separation, you will have this type of problem. So, to avoid the grating lobes, you must keep your spacing between the elements less than lambda. So, with proper selection of the elements, the bidirectional can be made unidirectional. Already I have explained you that if you are taking a dipole, obviously you will get a bidirectional situation. If you are not taking a dipole, a proper selection of the antenna will give a unidirectional radiation. There is another way to achieve this also. Place equal similar type of array, just a lambda by 4 distance, excite those elements with a phase difference of pi by 2. Then you will see that the lower side will get cancelled, only the upward lobe will exist. So, it is a parallel array you are putting below the original array. This is your original array, then another array you are putting. This array is lambda by 4 apart, then it will have a pi by 2 phase. If you calculate pi by lambda by 4 and pi by 2, almost all the backward lobe and the upward lobe, they will be meeting out of phase, they will cancel each other. So, only you will get a single lobe. So, this is type of situation also you can generate. Then comes another situation called the ordinary end fire array. This is again we are continuing with the pattern, that how the patterns are distributed based on the array, pattern distribution, the array is classified. So, the second class under this category is your ordinary end fire array. This is called ordinary because here the maximum direction contains a maximum field, does not necessarily a maximum directivity. So, it has been modified by another equation which gives maximum directivity in this particular type of array. So, that is why it is called ordinary array. The other one is called Hassen-Woodward conditions array. I will come to that situation. So, here the maximum radiation is along the array axis. So, like here you had a perpendicular situation, whereas in case of this you will have a situation like along the axis. So, that means either in this direction or in this direction or in both. So, it can be bidirectional. So, if I define this as 0 degree, this will be your 180 degree. So, that means in an end fire array you will get the maximum radiation either in the 0 degree direction or in 180 degree directions or in both of these. Here the phase changes progressively. If you put this condition here now, kd cos theta plus beta is equal to 0, because that is the maximum, always you will get the maximum, psi should be equal to 0. This implies that kd cos theta plus beta is equal to 0. Now, I want to look for a 0 degree maximum. So, my theta will be 0. So, if I substitute theta is equal to 0, then beta is equal to minus kd. So, depending once your RE is fabricated, d is fixed. So, looking into that d, now you must pick up your beta in such a way that that should be minus kd, so that you will get a end fire radiation and that too in 0 degree. Okay. If you are looking for, this is for 0 degree. If you are looking for 180, so it will be plus kd. So, this is the interlink between the space and the phase of excitation. And this is to show you that how the end fire will radiate. So, how the end fire array will radiate, you can just have a look. You have a radiations in the 0 degree directions with certain minor lobes coming on to the main lobe. Then similarly, you have a radiation which may be in 180 degree directions. Okay. Now, this, as already I have told you, in this situation, in the 0 degree or 180 degree, you may get maximum field, but this particular ordinary end fire array does not guarantee that maximum directivity will be in that direction. The fields are getting added up in 0 degree as well as 180 degree. In terms of the directivity, we cannot define that it will give a maximum directivity, even if usually it gets in that direction. So, now to increase the directivity of the ordinary end fire array, Hansen-Woodward suggested another conditions, and this condition says that instead of taking beta is equal to minus kd, take beta as minus kd plus pi by n, kd plus pi by n, where n is the total number of elements present in an array. So, and this particular thing was not theoretically found out, it is experimentally found out. After that, the condition was derived. So, otherwise the plus minus condition remains same. For 180 degree it is plus, for 0 degree it is minus, but with kd only pi by n you have to remember that once it is a directional enhancement of the array of the ordinary end fire, when you are talking in terms of the Hansen-Woodward condition, just a pi by n is getting added up to the ordinary conditions, and n is the number of elements. Here the directivity is a dependent function of the separation between the elements, and normal circumstances it is given as n minus 1 by n into lambda by 4, but Hansen-Woodward condition is valid for a large array when the distance is also large. So, when you are comparing a large array, obviously n minus 1 divided by n will be nearly equal to 1, because n minus 1 and n will be nearly equal. So, that is why the separation between the end fire array under a Hansen-Woodward condition is lambda by 4. Okay. So, the separation between the elements for this particular array, you will find that it is around lambda by 4, and this array, because of this pi by n addition, gives more than 70% enhancement in the directivity. Depending on your space, you will find that you are getting different type of enhancement in the directivity, 73%, 74%. When we will solve some problem in this direction, I will show you how it is done. Am I clear so far? Yes. Now, another class of array is called the phase shift or scanning array. So, as the name implies, here you are not fixing the lobe. The lobe is capable of shifting, that is squint in the lobes, so that the lobe is shifting as per your required direction, and you are in a position to scan the total required space. So, it is not along the 90 degree, not along the your 180 degree. Why? Because already you have seen two conditions. This beta, when it is 0, it is 90 degree. When this beta is equal to minus kd is 0 degree. When this beta is plus kd is your 180 degree. That means beta is a thing, beta which is within your control is a parameter which is helping you to shift the lobe. So, if this beta is taken different values, obviously it will give you the different shifting. So, same equation here. In a particular direction, when you are looking for, this should be 0 in that particular direction. So, let us say I am looking for 30 degree. So, I will get a beta value here for the 30 degree situation. Now, I am looking for a lobe in the 60 degree. So, I will get another beta for 60 degree. So, beta 30, beta 60, like that. If I put a table and accordingly feed the things like go on giving this type of phase shift, then obviously the lobe will go on shifting. Alright. So, you have a phase shift scan array. The array is scanning the space, and the beta is being controlled as minus kd cos theta. So, as per your theta requirement, you go on varying the beta value, because once the array is fabricated your D is fixed. So, D you cannot change. I will come, there are some new approach how D to be changed, all those things we will discuss once I finish this thing. These are the recent approach which reconfigurable antennas and those things which we have discussed, we will discuss later on. So, this is that original slide which I had shown you. This is basically to give you an idea that it is a phase shift array. That first if you look, this is generating in this direction, then gradually it is creating another direction, then another direction, like that you are having a situation of scanning in different direction. So, the shifting is from 0, 90, 270, 180 and any other direction in between this. So, like that you will get a phase shift array. So, now how to attend this phase shifting? How to attend this phase shifting? Basically, you use the ferrite phase shifter to achieve this thing. When the ferrite, as you know, you have a different wiring in this, when you send different current through this wire, this will go on changing the phase through the permeability variations, then the phase will go on shifting. As the phase shifted, your lobe will go on shifting. Even the diode phase shifters are also used. So, depending on your availability, you have to explore this possibility. But the recent approach in this direction is to explore the possibility of FPGA, so that you achieve the phase shifting or you achieve the shifting of the lobe without having a practical phase shifter. So, it is possible. It is now possible because there are certain paper in this direction 2005 onwards I have seen. In our lab also we have tried and it is working, but further studies are required in this direction to make it a foolproof situation. But the phase shifter now gradually going to be replaced with a new approach, and shortly the things will come to your limelight. So, this is a distribution which is based on the excitation. When you are going for phase, so from the pattern you have come to the control of the excitation approach. So, based on the excitation your array is also named as phase shift scan array or scanning array. There is another approach, another name for the antenna array, another type of antenna array you will come across, which is called collinear antenna array, where the antenna elements are stacked one above the others. Ek rakha, like this, like this, like this, it goes. So, and again this is a broadside antenna array approach. So, it is something like that. This is one element, this is another element, this is another element, like that they stack. This separation is between 0.3 to 0.5 lambda. Theoretically, if you keep this thing, then the antenna performance is good, but unfortunately, if you go for this, there is a feeding problem. So, if you are going for this type of separation, there is a feeding problem, because the separation and stacking situation creates a complex. Normally, this is just put on the top of an insulator. One of the antenna is top of the insulator, another is at the bottom of the